So this is going to be a video about kind of how to generally approach a proof. Again, this is usually talked about as an outline because it's not a uh, hard and fast, set in stone way of doing it. This stuff is a general guide, so if you're stuck on a certain portion of a proof or whatever, you can kind of see what your next move should be. Do not think that every proof has to go the exact same way every single time because it does not, and oftentimes it will not. But in general, I try to break down the steps to solving a proof in basically the three steps. Again, these are kind of broad steps because proofs takes more than three steps to do, but they help you guide. Um, so step one is housekeeping. So housekeeping is just getting rid of the basic stuff that we always know how to do. So definition of midpoint and bisector, which gets two things congruent. Definition of congruence to change them all into equal signs. Vertical, linear pair, complementary angles, anything that we need to say about the stuff that we can see right away that we're going to play off of later on. So this is like getting everything we know about the stuff just at a glance on the board, written down so that we can use it later, right? Step two is getting the pieces in place. So this usually means get the pieces that you want in place. So if you want to talk about segment AC, you want to get AC in place some way. Maybe it's a portion of a segment. Maybe it's a big angle that can be broken down to other angles. Don't know, but you want to get the pieces you want to talk about in the proof if they're not already. And then number three is to get the desired pieces in the same equation and link together, and then you simplify that equation, again, usually through substitution or your algebra properties, to get the two things that you want to be linked together. So let me show you kind of how I would approach that in a general setting with some proofs here, right? I'll have one angle, one segment. So given AB is congruent to CD and BC is congruent to DE, prove that AC is congruent to CE. So again, step one is housekeeping. Midpoints, bisectors, congruence, and special angles. Well, I don't have any special angles here since this is segment one. I do have midpoints though. Or sorry, I do have congruencies though. So I'll say AB, and again, pardon the poor handwriting. CD, and then we have BC, congruent to DE, and that's given. Okay. Now, this is when we would tackle midpoints. Remember, if like B was a midpoint, I'd say that AB is congruent to BC. But B is not a midpoint because I don't have any midpoints given to me, so I skip over the midpoint step. I do have to change these congruencies to equals, though. Again, this is just kind of basic housekeeping stuff. So I'm going to change them to equals because remember, we're going to be talking about the distances of these segments, so they should be in equal mode. CD, not in congruent mode because congruent mode is more about the segment itself. I hate when I click that button. DE. Has to get off there, sorry. And then that would be definition of congruence. We don't have any angles to take care of, obviously, so we can skip that part too. So again, the first steps is just taking care of the basics, right? Stuff that you do every single proof almost. Again, the tried and true basics. So we've gotten step one down. We've taken care of all the housekeeping. We don't have any midpoints or bisectors. We've taken care of all the congruencies, and we don't have any special angles. So the step two is get the pieces in play. So this is what I mean by get the pieces in play. I want to say something about AC and CE. That's the stuff I want to prove about. Well, AC isn't mentioned in this proof yet. Nowhere here have I mentioned AC. Same for CE. Nowhere in here have I mentioned CE. So I want to get them in play. So I go to my diagram and I say, okay, what can I say about AC to get it in play? Well, it's a segment made up of two pieces. So I can say that AC is equal to its sum, AB, plus BC. So if it's a big segment, what you can say about it is that it is the sum of the small segments that make it up. Same is true for CE. CE is equal to CD plus DE. Again, I'm getting the pieces in play here. And this is by segment addition postulate. Segment add postulate. So this is what I mean by, again, get my pieces in play. Now I have something about AC and CE that I can work with. There's something in the proof about those two things that I can manipulate, move around, and do what I need to. This is when I dive into the third step now, which is getting the desired pieces in the same equation or linked together. So I want to get AC linked with CE. Right now they're separate. I want them linked. So then you ask yourself, is AC and CE a compound segment? Are those two things made up of more than one segment? And your answer would be yes. AC is made up of two segments. CE is made up of two segments. So if I want to get them to be linked up, I need to get their DNAs to be the same. Well, this is CD and DE, but luckily I know that CD can be replaced with AB and DE can be replaced with BC. So I can replace CD with BC. I can replace DE. Sorry, wrong one. I can replace CB with AB. Technically, the order doesn't really matter because it's all commutative anyway, but I'll try to keep it nice and consistent. So CD can be replaced with AB because those two things are equal. DE can be replaced with BC because those two things are equal. That's still equal to AC. Now, what is this? Well, this reason would be called substitution because what I'm doing is I'm swapping out. I made another mistake. That should be CE. My bad. Sorry about that, folks. Because I am taking this equation. Let me make sure I say why I was wrong there. I'm taking this sum and turning it into this sum. So the sum total, CE, is staying the same. CE is not changing. Its DNA is changing. I'm swapping out its DNA with different pieces. And because I'm swapping, that is substitution. I'll write subs for short here. So usually in this step, you're going to do some sort of substitution or transitive property because usually when you get to this step here, you're swapping stuff around so that you can start establishing links between pieces. My goal is to show how pieces are the same or connected, and this is one way, is changing the DNA of big pieces to show that they're the same. Now, if this was reversed and I was trying to prove that, say, one of these small pieces is equal to one of these other small pieces, I would kind of start the same way. I'd still have segment addition postulate. Usually what happens in that case is that you know the big pieces are equal or you have some way of figuring that out, and then you can set their DNA equal to each other. So if you want to prove that the small pieces are congruent, it's going to be approached a little bit differently, but mostly the same. And so then now this kind of finishes up in a standard way. I have the DNA the same, so AB plus BC, AB plus BC. So that means that these two pieces, AC and CE, these two things have to be equal to each other because they have the same DNA. So I'd say, if this lets me scroll down, okay. For some reason, it's not letting me scroll, so we'll just go with it. So we can say AC is equal to CE by another substitution. Again, the reason this is substitution is because I am basically swapping out this DNA, AB and BC, with the thing itself, AC. So I'm taking this thing right here. I'll try to do it in a different color here. I'm taking this chunk right here, and I'm swapping it for AC. Now I'm putting AC first, but again, it doesn't matter which one comes first on the equal sign. So that's why I just have the two big segments. And then, of course, you would end it by saying the two things are congruent by definition of congruence. Since my program here is not letting me scroll for some reason, let me try one more thing here, see if I can't get it to function. Nope, it does not want me to scroll. Interesting. So I will write my final one over here. AC congruent to CE. Fumble fingers tonight. AC congruent to CE by definition of congruence. Definition of congruence, right? So again, same basic format, just a little bit. You need to be a little bit on your feet and adaptive when you get to certain stages. So again, if you had midpoint, obviously you'd do a midpoint before you do definition of congruence. If you had a bisector or stuff like that, you would take care of that in your housekeeping phase. So again, just to kind of adapt proof to proof. Whoops. And one more here for angles. So just to show you how it's similar for angles. So start the same way. We're going to write our given. I'll try to write small this time because evidently it does not let me scroll. So VZW congruent to XZY That's given. All right. Now again, we're still in the housekeeping stage, right? We're in step 1 right now. So I'm looking for midpoints, bisectors, anything I can change to be equals, and then special angles. So don't have any vertical angles. I don't have any linear pairs. Technically, all 3 of these angles would add to make a linear pair, quote unquote, even though it's more than 2. So all 3 of these would make a 180-degree angle, but I don't really need all 3 of them in this proof, so I'm not really going to bother with the fact that they all add up to 180. You could say that, you wouldn't be wrong, but it's just adding in extra information that you can't use anyway. Um, and I don't have any complementary angles because I don't have any right angles. So I don't have any special angles. I don't have any bisectors because it doesn't tell me anything about a bisector here. Remember, bisectors are kind of like midpoints for angles. So if I said that this line here was a bisector, I could say that this angle and this angle are congruent in my proof, and that could start a link that I could use. But I don't have a bisector here, so I just have to leave it be. And so that means that we're just going to go straight to taking care of our congruencies. So I'm going to say VZW is equal to XZY by definition of congruence. Again, if you don't have any midpoints or bisectors, you should just go straight to definition of congruence in most cases. Now again, I need to get my pieces in play. So I need to get big angle here, WZY, and big angle here, XZV, in place some way. So let's go here, WZY. So that's this big angle right here between these 3 letters. So that's made up of angle WZX, this guy right here. So WZY. Notice I'm using 3 letters for an angle like we always do. So that's an angle symbol, by the way, that I just drew. Trying to get it a little bit better. WZY is equal to angle WZX plus angle XZY. Keep hitting that button. There you go. So XZY. And that is because angle addition postulate. Angle addition postulate. Again, pardon the poor handwriting. I am writing with the mouse after all. There we go. So angle addition postulate tells me that the big angle can be summed together with the 2 small angles. Now again, I also have to get in XZV. So XZV, I'm going to look at that and say, what can I say about that guy? Well, similarly, it's another angle sum. So XZV is equal to XZW. Actually, I'm going to write the same way I did last time, just to show you something. So this angle right here that I'm looking at, I could call XZW, but I already labeled it as WZX up here. So I want to kind of keep that the same thing, WZX. So again, if you notice yourself labeling something backwards that you've already labeled forwards, you might want to change it because that just helps your analysis. And then the last one is WZV or VZW, which I haven't used yet, so I can label it however I want. So WZV. Actually, I did label that. My bad. We already had that labeled as VZW. So again, let me be consistent. VZW. VZW. Same angle, just written differently because we already wrote it once up there, and I don't want to contradict what we've already written. All right. So now I've taken care of my getting pieces in play. Every piece I want to talk about is in play in some way, shape, or form. So now I need to get them linked up. Well, again, I notice here WZY and XZV are compound angles, aka they're made up of 2 smaller angles, which is why I got their DNA. And so therefore, if I want them to be equal, I need to get their DNA equal to each other. That's how I'm going to get them linked. So I'm going to look at my stuff here and say, oh, well, part of their DNA is already the same. So they both share at least 1 angle, right? That's good enough. It's these 2 angles that are causing me issues because they're not the same. Well, luckily, I can show that this can be replaced with this because the 2 things are equal based on my given. So it would look something like this. If I look at the top one here, WZY is equal to WZX plus VZW because of substitution. Again, I'm swapping this guy out for this angle over here to show you that, hey, their DNA is actually the same. It didn't look the same before, but now the DNA pretty clearly between the blue and the green stuff, that is definitely the same DNA. And so that means that definitely the big angles are equal to each other. So I can say that XZV, whoops, XZV, not XZW. XZV is equal to angle WZY. And again, this is by substitution. Don't be afraid of using the same reason back to back. Now, if you use it back to back 9 times, we might have an issue. But if you use it back to back once or twice in a proof, it's still okay in most cases. And then, of course, we'd want them to be congruent just to finish it like nice geometry students. It's congruent to WZY. And the reason is by definition of congruence. And that's usually how we're going to end proofs in most cases here. So this video, again, wasn't meant to be a completely alleviating thing. It was just meant for those that just need a little bit more extra explanation or a little bit more examples about how to work a proof. And again, just keep in mind these 3 things. Housekeeping, get pieces in play, and then get those pieces linked up in some way. Because if you get them linked up, from there on out, it's usually just substitution and a little bit of algebra. But you need to make sure that you get them linked up first. Again, usually using segment addition posture or something like that. So, that's the end of this video. Hopefully it helps you out. If you have any questions, let me know. Otherwise, have a good day.